Okay, welcome to the today's class. Today we are going to look at lecture number 13. That is small signal model of nMOS. Small signal model of MOSFET. A small signal model of a MOSFET. Okay. So far we have seen that long channel MOSFET behavior. Okay. So what is the long channel behavior MOSFET behavior? Uh, for example, if you take for a long channel, let us consider nMOS N channel transistor for a long channel device, nMOS and MOSFET. We have seen that the ID value is defined by IDS value can be defined by mu n C of W by L into VGS minus of VT n into VDS minus of VDS squared by 2. Okay. Under the condition of VGS value is greater than VTH. Not only that one, VDS value is less than VGS minus of VTH. So this is what the behavior that we have seen. Okay, it's a linear relationship. As long as we are increase the VDS, IDS also will increase the same way. Next one is IDS is actually, it's not true that every time that is happening. At certain voltage, the MOSFET behaves as a saturation, will enter into the saturation, means that it's independent of VDS changes. Okay, therefore, then in this case, we are going to write, we have derived this one in this way, VGS minus of VT n whole square. So provided that VGS must be greater than or equal to VTH, not only that one, VGS is greater than or equal to VGS minus of VTH. Okay, of course, it's also just a threshold voltage is enough to make the transistors on. Okay, this is what the MOSFET that we have seen so far, right? It's the gate, drain, and source. Okay, so we have seen that the current flowing here is nothing but IDS. Okay, but actually we are going to use this MOSFET mainly for the purpose of amplification, right? Mainly for the purpose of amplification. What do you mean by an amplifier? What do you mean by an amplifier? A small definition about the amplifier. Whenever you give a signal, the signal power must be enhanced at the output node. Okay, whenever you give the less strength signal, the strength of the signal must be more at the output side. In fact, the power actually. Okay, in fact, the power. Okay, so power enhancement can be done by the amplifier. Okay, power enhancement. Power of the signal will be enhanced. Okay, not only that only the voltage will be amplified, but the power of the power of the signal must be amplified. That means when the power is that much V into I, the both parameters V as well as I also has to be enhanced at the output node for enhancement. Okay. Now, so we are going to use this MOSFET for the purpose of amplification. Okay. That means, look at this one, the input side, we have to apply a small change. Okay. Okay, let me consider it here in this way. If this is the MOSFET, okay, and this is what we are applying VGS, gate to source voltage we are applying here. This is a gate, let me call this a drain, this is a source. We are applying the gate to source voltage and we are getting the IDS value, right? That's what we are getting. We get the IDS. So this is called the quiescent voltage also, we can say that. That means the VGS value for the large values of the VDS, how the IDS will be changes that we normally consider. When we talk about the amplification, we apply a small signal, okay? A small input signal that we have to apply. That means there is a small change in the VGS, a small change in the VGS we apply, okay? How much change in IDS that we will get, that's what our intention is. Okay, so therefore, before applying this, the MOSFET in the amplification, first look at how the MOSFET will behave for a small change. How it will behave as a small change. For example, the VGS is 1 volt, for example. For example, it is a 1 volt. Okay, assuming that this is, for example, 0.1. Okay, for example, yeah, 1 milli. For example, this is called 1 milli, 1 millivolt. So this is a small change. Okay, 1 milli in 1 volt to 1 millivolt is very, very small change. Okay, so for the small change, how the MOSFET will behave, that's what we would like to understand. But generally, what happens if you see, the inherently the MOSFET is actually very complicated device. And one more thing is it's a non-linear device. It is a non-linear device because sometimes it's a linear, sometimes a non-linear. Okay, so then definitely it is a non-linear device. MOSFET is okay. So this non-linear device, how the non-linear device behaves for a small changes of the input or small changes, how it will behave. Okay, so under the small changes, okay, under the small changes, under the small changes, the MOSFET behaves as a linear device. A linear device. Okay. Under the small changes, okay, we consider it in this way. Okay, if it is a linear device, then we can replace this non-linear transistor as a linear element, as a linear circuit. Okay, how do we represent this? How do we convert this particular non-linear element into a linear element? Okay, for the small changes. This is actually applicable only for the small changes, not for the large changes of the signal. Okay, so as I mentioned, that the small change is nothing but when we talk about it's a 1 volt, the small change can be 1 millivolt. Okay, so that means that we have to replace this MOS transistor with something. Okay, let me consider this is the gate, this is the drain, this is the source. Of course, the body is also available. Let me consider this is also a body, for example. Okay, how this MOSFET will be realized with linear elements. Okay, so this is the one case actually when we are applying the VGS, a small change in VGS, IDS also will changes. Let me consider this is okay. The change of the delta VGS can be called as, for the simplicity, I'm writing as a small VGS. What do you mean by a small VGS stands for? A small. Okay. Look at here also. Here also we'll write as a small IDS, small ID. Let me consider small ID. Yes, it's no need not to say that one. Okay, ID is a incremental.
okay, or a change. Okay. So therefore, the incremental value of the VGS is nothing but small VGS. Incremental ID is actually small IDS. Or I can say that the small change we can call it as small VGS. Small increment, the change in the IDS is nothing but a small change in the IDS is nothing but okay. So therefore, one parameter that we can see, ID is actually influenced by what VGS. What are the other parameters can influence the ID? For example, source. That means source. That's why I talk about the potential difference. Okay, I'm talking about the potential difference, not only one particular point. The potential difference between the gate and source is able to change the drain to source current. Is there any other potential difference will change the IDS value? A small change in something will result. As we can see that, for example, VDS, for example, okay, VDS, for example, if you apply a small change in the VDS, for example, okay, a small change in the VDS, then it is also possible to change ID. Of course, if it is an ideal condition that the transistors operate in the saturation region, definitely IDS is not a function of the VGS, function of the ID, but let us assume that the channel length modulation is considered. Okay, under the channel length modulation, when the VDS changes, the current value also changes linearly. That's what we have seen in the second order effects, right? Okay. Now that is another parameter. Okay, that means a small change in this one also will responsible. That means a small VDS. Whenever the moment if I'm writing the small letters, what you have to remember? A change, a small change. Okay, right. So, and there is a possibility that the body is also body, for example. Okay. Therefore, if you change this VBS with a small change in the VBS, for example, a small change here, this also can influence the ID value. Why? Because when the gate to source potential is, sorry, body to source potential is different, if they are not at the same potential, if they are different, then definitely what will happen? The threshold voltage of a transistor will changes. Because of the threshold voltage, the ID values also will get changed, right? So these are the three parameters. These are the three parameters we are able to see that ID will change, right? Therefore, VBS. Therefore, IDS is actually a function of IDS is a function of VGS change, VDS, as well as VBS as well. Is this point is clear to everyone? Okay. So therefore, I can say that little bit I can write it in this way also. Small ID is actually a function of the changes in the VGS, the changes in the VBS, sorry, DS, and change in the body to source. Agreed? A small changes. As I mentioned that very small changes, the MOSFET can be replaced with an equivalent linear circuit. So let us develop what is the linear circuit or a small signal circuit that can accommodate this kind of behavior. Okay, let us look at this. Let me write the first case. The first one is influence of VCS on IDS. Okay, first let us consider it in this way. What is the influence of VCS on IDS? Okay.
So look at this point. Okay, we have a transistor here.
Let us apply a small VGS here. What I can observe, there is a ID, sorry, there is a small change in ID because of the VGS, right? ID is because of the VGS. See, I'm applying the small change VGS. Of course, what is the total current? Total change means what? What is the total value of this one? That means this is the one where I can say that, okay, first of all, you write VGS, you'll get some IDS, the larger values of VGS, and we'll get the large value of the IDS. And by applying the small VGS, you will get the small ID. So adding the small IDS and the small IDS and the big IDS both together, it will be a result of that. Okay. But actually, that result is a very nominal. Okay. But when we talk about the amplification point of view, it's a very, very big thing that we will see a little bit later, right? Okay. But anyway, by applying a small change in VGS, we are getting some kind of change at the output. So what we can, what fundamentally we can write it, this is.
That means we are applying VGS, right? What we are getting? Okay, sorry. What we are getting actually IDS ID that we are getting because of what? VGS.
Okay. Because of VGS. When the VGS is increases, IDs also will increase. Okay. So therefore, what is the proportionality constant here? What is the proportionality constant? Let me understand this one. Normally, simply a fundamental equation is that since we know very well about that, okay, V is equal to I into R, okay, V is equal to I into R. Then I is equal to what? I is equal 1 by R times of V. That's what we know very well. So therefore, what is the proportionality constant here? 1 by R simply. Simply 1 by R. So therefore, now what we can call it as R nothing but a resistance, right? R is nothing but a resistance. What is 1 by R? What is 1 by R? It's a conductance. 1 by R is nothing but a conductance. Okay, conductance. So this is 1 by R is also called as conductance, that is also called as GM. Is also called as GM. So exclusively this GM is called transconductance. What this is called? Transconductance. Why it is a transconductance?
So we are taking a one parameter. VGS is at the input side, at the one side, and we are observing the quantity at the other side. Okay, that's why it is called transconductance. Therefore, we talk about a transconductance. Therefore, now I can simply write ID is equal to GM times VDS, VGS. Can I write like this? Okay. The moment I'm applying the VGS, I'm getting some amount of the current, but that current is proportional to what? It's proportional to GM. Okay, sorry, VGS.
Okay, that means I can simply, the moment look at this one, the gate is actually here. So gate to source is actually, so gate to source, what is the amount that we are applying here? VGS I'm applying here. A small change. Therefore, this is a gate, this is a source. Let me consider this is a source. Okay. Gate to source I'm applying. And what is the thing that I'm getting here? I'm getting some amount of the current. Okay. It is just like a current. It's a dependent current. What is this one actually? It's a dependent current. Why it is a dependent current? This current is depending upon the VCS value. Therefore, can I replace and write this one as
GM times of VGS, right? This is what we can write it. Okay.
So this is what IDS. What is the IDS here now? So this IDS is actually IDS, sorry, let me write it the lowercase letters. ID because of VGS. That is the one current that is developed, right? Therefore, for example, if you want to have a more current, for example, then which one is the responsible parameter here? The device parameter is most important. Okay.
Apply a small potential here. VGS is a small thing that you have applied. Okay, but you want to have a more current. Then what you have to do? We have to multiplication factor. We have to use it. What is the multiplication factor here? Transconductance GM. If the GM of the transistor is more and more, what you can get? More current will be possible. That is what's essential for the amplification. Okay, a small change of something must result in more current. We pass that more current into a large resistance path, then it will enhance the power. What is the idea of the amplification? So we are converting the voltage into a current, okay? A small voltage into a big current, large current, and that large current we are passing through the resistance, a large resistance path, then we automatically get more power. The power enhancement can be possible. Okay, that's the reason why we always try to get the more current. How we are getting the more current? By the transconductance of the amplifier. If you're increasing the transconductance of the amplifier, sorry, if you increase the transconductance of the device,
then you obviously will get more current. Okay. So what is the transconductance of a transistor? We have derived previously. What are the things? How we have defined the GM?
Different three options that are there. One is, let me write here, mu Cox W by L. But how do we get this particular one? Can anyone help me? What is the root way that we have to get this GM? GM is derived by, yes, very good. Dou ID divided by dou VGS. So that's how we'll get. So what is where we will get the maximum current? At the saturation region, not in the linear region. We have already, I told you that point also. Okay, in the saturation region, we'll get a more transconductance. Okay, that means a small VGS will get a more current that can be possible. That's the reason why the MOSFET must operate in the saturation region for the amplification purpose. Because for the amplification purpose, so more transconductance is required. If you where you will get the more conductance, you have to operate when you are operating the saturation region only, right? Okay. So therefore, we will get in the saturation. What is the value that we got here now? After so many things, we concluded that VGS into VCS minus of VTN. Okay, as you can see, the transconductance of the transistor is depends upon the large value of the VGS, the main value of the VGS. Did you catch this point? Not the small value. Small VGS not depending upon. It depends upon the capital VGS, not small VGS. Please remember that. Okay.
Or what is another option?
What is another option? That is a 2ID. All right. 2ID divided by VGS minus of VTN. This is also one possibility. Is it? Or otherwise, we have another possibility. Square root of 2 mu n Cox W by L into I.
So therefore, if you want to calculate the GM, it's completely depending upon
the device dimensions,
okay, as well as the quiescent voltage or quiescent parameters. Quiescent voltage means that the large values of that.
Okay, as simply we can understand about this. Okay, ideas, something like this. Hopefully you catch this point. Okay, so simply this is what actually
this is what simply we can call it as drain. So forget about for the time being the body importance here. So this is what the small signal model of an nMOS transistor. It is a small signal model of an nMOS transistor. That means whenever you have a MOSFET, you can replace this MOSFET as something like this by applying the small transistor.
Okay. Can we apply it for the large VGS? Is this particular model is applicable for the large changes of the VGS? No. Okay. A small changes of the VGS only this is applicable. So this is under saturation condition. Okay. If somebody asks you, can you please draw the small signal model of a MOSFET under the saturation region? Means that you have to draw this. Okay. Point is clear? Right.
So this is what the transconductance. We talked about the transconductance. This is the one parameter you have to remember in the small signal analysis. Okay, right. Next, let us look at some other point. Influence of VDS on IDS. Okay, what we can call it as influence of VDS on IDS. Okay, now as we know very well that because the MOSFET is operated in where saturation region, everybody knows about that. Okay, if you want to go for amplification and analog applications, MOSFET must be operated in the saturation region. As we know very well that this is how the behavior is. As you can see, so the ID value is constant throughout this region, right? Okay, so the moment if you cross this particular point, okay, so as long as VDS is as much as VDS is we apply, the IDS is constant. That's what we have seen. Okay, but generally, when we use the channel length modulation, okay, because non-linearity will always come into the picture. When the device dimensions are lower and lower, okay, the channel length is smaller and smaller, definitely the second order effect, the channel length modulation will come into the picture, undoubtedly. Okay, so under that condition, how you can, a small change of the VGS, sorry, a small change of VDS, how it will influence the current we have to find. Okay, that's also an important one. Okay, the friends, this is what we can see under the channel length modulation. So instead of this is a constant something like this, it will go in this way. Okay, so therefore how it is increasing, this is defined by the resistance of this one, right? So we have to calculate the resistance of this one. So the slope of this one is nothing but a resistance, right? The slope of this line is actually a resistance. So this resistance we call it as a output resistance or not. What we can call it as output resistance. Okay. So therefore, now we'll look at this particular one. Whenever we have a MOSFET here, it's a drain, this is the source, this is the gate. When we apply a small change here, nothing but VDS, and there is a possibility of flowing the current here, that is called ID. This is nothing but this is due to because of VDS. This is due to because of VDS. Because we have taken the channel modulation, right? Now, how do we how can we replace this MOSFET under this condition?
there's a question. In the previous case, when the small change of the VGS result in the IDS, therefore we replace that one with the help of a constant current source, dependent current source we have replaced. Now, how can we replace this MOSFET for this behavior? Okay, how do we do this one? So let us go in this similarly. Okay, therefore what we are expecting that IDS we will get is proportional to the again VDS. Okay, but normally these two quantities are at the output side. Okay, therefore we can also write something like this. Okay, since how much the current is flowing is defined by the resistance value here, therefore here we can write it here also. IDS is proportional is equal to 1 by R times VDS.
Okay. Now it is writing is also written in this way. Since it is a small signal understanding, let me write R naught is this one. Okay, R naught is nothing but how do we define this one? VDS divided by IDS. Am I right? VDS divided by IDS. Please remember that whenever moment I'm writing the small letters, it is a changes actually. What is this change here actually?
What is the meaning of this one? I VDS divided by dou IDS. This is what actually the real meaning of this one. Okay, so but we cannot calculate VDS with respect to IDS, but we can calculate IDS versus VDS. Am I right or not? Okay. Therefore, how do we write this one? 1 divided by dou
IDS divided by dou VDS. Can I write like this? Can I write like this? Right. Okay. So now how do we calculate this one? How do we get this particular parameter R naught? That means, yeah, one point let us consider about this. Whenever we have a MOSFET that can be replaced as a small resistance R naught, not small resistance, some resistance R naught under small change in the
VDS. Under the small change to the VDS, we can replace MOSFET as a small the resistance value, output resistance. Okay, so now let us look at what is R naught. As you know that according to this particular definition, what kind of equation that I have to consider?
dou by dou VDS 1 by 2 mu n Cox
W by L into VGS minus of VTN whole square into 1 plus lambda times of VDS. Did you catch this point?
Okay. So we have to consider the channel length modulation. Unless otherwise there is no, if there is no channel length modulation, you need to consider about R naught. Okay. Right. So what about this particular value? What you can observe? 1 divided by 1 by 2 mu n Cox W by L into VGS minus of VT whole squared into lambda. That's it. With respect to VDS only we have to do, not VGS, right? So the derivative of this whole thing is not necessary to consider.
But only 1 plus lambda times of VDS. The derivative of constant is 0. The derivative of lambda times of VDS is lambda. Okay. So this is simply 1 by lambda times of ID. It's simply lambda ID. So of mu and C oxygen W by N VGS minus VT squared. But ID only is a VT. In this point is clear. Okay. Now how this small signal model will be evaluated now. So there is some current will be flowing. Okay. There is some current is flowing. That current is defined by, further I'm adding here. How can I replace the MOSFET? If the channel length modulation is there, then how can I replace the MOSFET? by simply a resistance. Okay, what is the value of the R naught? What is here R naught? What is the value of the R naught? 1 by lambda times of capital ID. That means this value is depending upon the big ID. Okay, the quiescent value of the ID. We call it as this way. Hopefully, did you catch this point? What is this current actually? This current is actually, this is ID over VDS. Right. Okay. Now, so therefore, this is called another parameter we normally call it as output resistance. Output resistance. This is another parameter we look at this particular way. Okay. Next, what is the last thing? Influence of VBS on IDS. Okay, that is another parameter also we can consider. Okay, because only these are the three things only can influence the IDS value. Okay, now our question is the analysis is the same because we take a MOSFET. Okay, there is a body here. Okay, now this is the body, this is the source. Okay, if you apply a small change here that is called VBS, then VBS I'm applying, then how much current will flow? That is what I can, how much amount of the current is changes. ID of VBS. Okay. So that means if under this condition also we need to replace the MOS transistor some kind of equivalent for the small changes. Okay. So the small change is the VDS, how it will influence the ID. Okay. Can someone help me? What is the meaning of this one? Here also we normally considered as ID is proportional to what? VBS, right? What is the proportionality constant? Here also you can see one is at one port, one side, another is at another side. Okay. Therefore, this is actually at one side. This is actually at the other side. It is also just like a conductance only. It is also just like a conductance. The conductance is also as a trans conductance. But this conductance normally we can call it as a body trans conductance. What we can call it as body trans conductance. Therefore, we simply write it here is ID is equal to GMB into VBS. GM into VBS. Can I write like this? Yes, right. Now, how do we calculate the GMB? How do we calculate the GMB? ID divided by VBS. What is the meaning of this one? The meaning of this one is dou IDS divided by dou VBS. Okay, but we have no choice that no VBS is related to the IDS. So far, whatever the equations that we have seen, we have not seen that, but it is derived something like this. So something like this: dou IDS divided by dou VTH. First, you have to derive with respect to the threshold voltage, multiply with dou VTH, because VTH value that we know very well. Okay, that big equation that is there, right? Okay, that equation with respect to dou VBS. Okay, VTH will get cancelled. The result will be something like that. Okay, now how do we calculate dou IDS divided by dou VTH. What is the value? Dou of 1 by 2 into mu n Cox W by L into VGS minus of VTN whole square. We have to do this one with respect to dou VTH. Can you someone help me? What is this? One by two, 2 will get cancelled. The derivative of this one is minus 1. Okay. This is actually, can I write like this, minus GM? Okay. It's just like a GM only. But actually it's a minus 0. No confusion, right? Okay. Now what is the second one? The second one is dou VTH divided by dou VBS. Okay. So what is the VTH here now? We have already seen VH naught some constant, body effect coefficient into square root of magnitude of 2 pi f plus VSB. Look at this one. It's a VSB, not VS. VSB minus of square root of magnitude of 2 pi f. Okay. With respect to what we have to do? With respect to VBS. With respect to VBS. Okay. Now what is the thing? What is the derivative of this one? The derivative of VTH is equal constant is 0. Therefore, the value of this one is gamma. So the root of x is nothing but 1 by 2 root x. Okay. So therefore, this is called 1 by 2 root 1 by 2 root magnitude of pi f plus VSB. Okay. Into, so we would like to get the VBS, but it is there in the VSB. That means the reverse is there, right? We have to take the minus. We have to take minus. Okay. Therefore, what is the value of this one now becomes? Minus gamma divided by 2 root magnitude of 2 pi f plus VSB. Okay. These two must be multiplied. We will get GMB is equal, minus will get cancelled. Okay, sorry, will become plus. What is this value? GM into R divided by 2 times of square root of magnitude of 2 pi f plus VSB. So therefore here also it's depending upon the quiescent value. Okay. But anyway, that what we can observe this one, it is a current source only. We can see here is the current source only we talk about, right? As you can see, this is simply a current source. Right? Therefore, we can replace the MOSFET with respect to by using the dependent current source, where it's depending upon VGS. Okay. Let me modify this diagram. Okay. Let me modify this diagram. Copy. Paste here. Right. Okay. So what is this drain here actually? So definitely, let me write the D somewhere else here. The D here. Huh? The source is here. As we can see that the source is available at the middle. Okay, for the sake of simplicity, it is in the negative side. It is in the negative. So where is the body? Body, let me consider the body is here. Okay, this is the body. This is the positive side. Okay, therefore VBS. Okay, therefore what we can see here, it's a VBS. It's a VGS. Okay, now what we can observe here, it is nothing but dependent current source. What is its value? GMB times VBS. Okay. So what is the small voltage that is applying here? So this is actually VDS. Okay. Of course, so let me consider the variations here. VDS. Okay. Because of this small VDS, what will happen? This is what is the result. Okay. Did you catch that point? Okay. Because of this one, what will happen? This is the result. Okay. Next, because of, for example, because of this, what will happen? Because of this, what will happen? This is what. Okay. This is what the small signal model of an nMOS transistor. Okay. Right. If I say that, for example, please draw the small signal model of an nMOS transistor by lambda is equal to 0 and gamma is equal to 0. What is the small signal model then? The case is, for example, what is the case I'm talking about? Note. Small signal model when gamma is equal to 0 and lambda is equal to 0. What does it mean? Gamma is 0 means what? No body effect. No body effect means we are not applying any VBS. If you're not applying any VBS, then there is no change in the IDS. Therefore, this will be considered as, let me take, this is what actually, let me consider this, copy. Okay, under this condition, what will be there in this one? Okay, so I don't want to consider this particular one. No body effect means this is not there. No channel length modulation is, this is also not there. There's simply this one only. Okay, no need to consider this one also. Agreed? If I say that only channel length modulation is considered, okay, but channel length modulation is not, this one is not considered. Sorry, only consider the body effect, but don't consider the channel length modulation. Then how the circuit becomes? Which one you have to consider? Not only this dependent source, what you have to consider? Which resistance or current source? Current source you have to consider. That means we have to consider the current source. What is this value? GMB times, VDS. Okay. So if I ask you the reverse side, for example, okay, not this one, but this is actually not equal to 0, but this is equal to 0. Channel length modulation is not, I'm so sorry. In the last case is actually wrong, right? Okay, this is what actually consider. This is what the correct for this one. Okay. If I take the reverse side, if the channel length modulation is, if the body effect is 0, but channel length modulation is not equal to 0, then what I have to do? I have to replace this one and I have to use a resistance value, R0. If this point is clear to everyone? This is value, this is the linear circuit actually. So whatever you can see, this is a linear circuit. Okay. So dependent sources are linear elements. Resistance is a linear element. Therefore, this is valid only under the small changes of the parameters. Please remember that one. If you're applying this one, applying the large changes of this one, is it valid means that it's a meaningless thing. Okay, it won't work. Okay, so therefore, this is another parameter name. Let me call this is the parameter name is body transconductance. Body transconductance. Okay. So usually for our analysis for the point of view, we consider for the body effect is no body effect and no channel length modulation. Under that condition, MOSFET is actually only having the
MOSFET is only having the dependent source only, one dependent source. Okay. Hopefully you catch this point about the small signal model of a MOS transistor. So we close now this time.